class, for exams, alright? Alright, so non-metals are elements that are normally found in group 5, 6, 7 of the periodic table. So the elements, so non are elements four, carbon is in group 4, right? And non-metal 4, 5, 6, 7, and the noble gas and group 0, right? The noble gases are also classified as non-metals, such as helium, argon, and those gases, alright? Now, so the examples that we have here, hydrogen, so we can look at some examples. Hydrogen, chlorine, oxygen, carbon. Carbon, sulfur, and nitrogen, right? Alright? So when you write like H2Cl2, this is how the element would normally exist in nature. Alright? So you won't find a hydrogen atom by itself in its pure form. It's always combined with another hydrogen atom to form a hydrogen gas. Right? That's how it exists in nature, right? As a pure compound, as a pure element, that is. Clear? So chlorine as a pure element is Cl2, oxygen is O2, and we know we find that in the air, oxygen gas as an element, right? Remember that element is just one particular type of atom exists together, alright? And carbon, we would find as either graphite or diamond, but that's pure carbon. Just carbon atoms bind together, right? So it's not really a diatomic molecule, and we don't want to put a subscript here because it's like unlimited amount of them can combine as graphite or diamond, alright? Sulfur again, sulfur mainly exists as S8, S6 allotrope, but at this level you don't need to just know that sulfur by itself. It's a solid, and it's like not gas in the atmosphere. It's non-metal but solid at room temperature. Nitrogen here again is a gas, which would be the most abundant gas in the atmosphere. Clear? So these are some of the elements that you can know. Some of the general physical properties of non-metal. So physical properties of non-metal. Right, so they can be solid, liquid, or gas at room temperature, right? Right? So unlike the metals in which they mainly exist as solid at room temperature, except mercury, which would be a liquid for metals, non-metals basically solid, liquid, or gas, right? So as I said before, most of these stuff they are gases at room temperature. Then you have bromine would be a liquid, Br2 that I did right here is a brown liquid, and sulfur is a solid. So there you will see example, it can exist as solid, liquid, or gas at room temperature. Alright? Varies. Alright? Other properties, they do not conduct electricity except carbon in graphite, right? So they do not conduct electricity or heat don't conduct electricity or heat except carbon, but carbon, as I said before, it exists as two different forms in nature. It's only the graphite form, right? Carbon in graphite. Alright? They tend to be dull. So unlike the metals which are shiny, they tend to have dull appearance. They have low melting and boiling points. Alright? And just to divert to explain the melting and boiling point issue here is that why they have low melting and boiling point, even though non-metals bond among each other tend to be covalent, which is a strong bond, they normally exist as small molecules. So for example, we have oxygen molecule. When we are, say for example, we have liquid oxygen or liquid nitrogen, since you may be familiar with liquid nitrogen, even though liquid oxygen used in the hospital. But say for example, liquid nitrogen. If you are boiling liquid nitrogen, to form from liquid to gas, it's not the nitrogen triple bond that you are breaking. You are just breaking the intermolecular forces between nitrogen molecules, right? So that is why we tend to have low melting and boiling point for non-metals, right? Unlike metals or ionic compounds, to boil or melt those substances, you actually have to break the metallic bond between the metals. So if we have a pure piece of like a sodium metal or iron metal with the atoms together in that metallic bond, you will have to actually be breaking the atoms away from each other from the sea of electron in metals. Or for ionic compounds, you will have to actually be breaking up the crystal lattice. Right? So non-metals is just the intermolecular forces, which are normally weak, very weak interaction between the molecules we need to break down. Right? Some molecules, some compounds such as water may have a little stronger force in between the molecules. That is why water is a liquid at room temperature, even though it's such a small molecule, which in essence, based on the size and the mass, it should have been a gas at room temperature. But because of you have stronger bonds, hydrogen bonds, it's actually a polar molecule. So the interaction between the molecules is a little stronger than normal because of those polarity, right? It forms what we call the hydrogen bonds in water, right? Even though you don't have to focus much on that at CSEC, you can at least be familiar with the term. So if you're writing something, the exam might sound intelligent and advanced, right? They also have low density. So non-metals, they have low density. So unlike metals, which if you put them in water, they will sink, some non-metals, the density might be so low that they might even float in water. Alright? They are normally, the solids are normally weak and brittle. So you can break down. Say for example, a good example of what that you might use as a baseline for weak and brittle is like the graphite, the pencil point graphite. That's how non-metal solid would stay. So even if you look at sulfur, that's why it will be brittle and soft, right? As I said before, the only exception would be diamond in the allotrope of carbon, in which it's a special case of arrangement which actually makes it very strong. It's an exception to the principles of non-metals, right? So if we're looking at the general physical properties of non-metal, it's like diamond in the carbon in the form of diamond would always be an exception from all those rules, alright, in terms of the strength. And in terms of the graphite would be an exception because it conducts electricity, alright? So carbon is kind of an exception when it comes down to the physical properties of non-metals, alright? In both forms, it actually have some slight differences. Stuff about so hydrogen is a colorless gas at room temperature, colorless, odorless, tasteless gas, right? And it is insoluble in water, and it's less dense than air. Alright. So when we talk about less dense than air, we have to know that air is mainly made up of nitrogen and oxygen, right? So if, for example, we look at the component of air and we check the mass, So air is basically nitrogen and oxygen. I think this is 21%, this is 78%. That's correct? Good. So if you notice the molar mass, we're going to go back to some moles now. The molar of nitrogen would be 28, right? 14 and 14 is 28. The molar O2 would be 32. Alright? No. So the nitrogen oxygen would be the major component of air. So for example, if you do an average there, this is roughly about 30 grams per mole, an average. That's a rough average. It's probably closer to 28, like about 29, since this is a larger portion, right? So if we have hydrogen, which is just 2 grams per mole, or we have oxygen, which would be 32 grams. We have a chlorine gas, 35 and 35, that would be about 70 grams approximately. Alright? In terms of the density, this is how you would determine which gas is more dense or less dense than air. Right? So if the relative molar mass is lower than the average for the air, it would be less dense. So like a hydrogen gas, if we prepare a hydrogen gas solution in a container with air, it would displace the air downwards. Right? So the hydrogen would stay at the top. Likewise, if we should prepare chlorine gas, right, it is more dense than air, so it actually would stay at the bottom. Alright, so we'd have to ensure that it's the gas would be escaping at the top. The air would escape at the top while the chlorine would build up at the bottom, then you seal it off. So the exit point would have to, because what happens is that if we should set the exit point where say for example in oxygen, if we should let the gas enter from the top, it would basically not displace and go down because it would actually be lighter than air. Alright? It would have to enter from the bottom and the gas would escape. The gas would escape at the bottom. So you enter it from the bottom, then it would displace the air out. Alright? You can further read into, or when we reach the preparation of gas, you will get a better understanding. Alright? Now, so oxygen, also a colorless, odorless, tasteless gas at room temperature, and it is slightly soluble in water, right? Reason being, you can remember oxygen. All living organisms need oxygen. So all the fish in this ocean and the river would need oxygen. So you can use that to remember that oxygen must be at least slightly soluble in water. Because remember that the gills from the fish, they actually use the gill would act as the lung in mammals. So the gill is actually to really absorb the oxygen from the water for respiration in the fish or in aquatic organisms. Alright? And as I said before, sulfur is a solid at room temperature and it's yellow in color. So sulfur, solid at room temperature. So it's solid. It's yellow. Alright? Oxygen is colorless. Tasteless, alright? Parts, right? But I'm just going to introduce a basic concept that I'm not going to spend much time, so even if you don't understand it, we're still going to have an entire class to discuss redox reaction. I just want to point out a few things to note when we're talking about redox reaction, right? So you have to know about reducing agent and oxidizing agent, right? So I said before, the syllabus was probably designed to teach the principles of chemistry first, before the organic and inorganic, right? But because I don't want to leave it close to the exam, I teach it this way, alright? So, oxidation If they're colorless, odorless, and tasteless. For oxygen, nitrogen, hydrogen. Alright? It will be the same thing in the air. Alright? Even carbon dioxide. Carbon dioxide, I guess, in the air. You're not tasting anything when you're speaking, you're not seeing it, and you're not smelling anything. Alright? So just know that all the gases in the air, they are colorless, odorless, and tasteless. That makes up air. And carbon dioxide is actually a gas in the atmosphere as well, even though it's a small percentage, but it's still there. Alright? And then if you want to think about like chlorine, maybe like a yellow gas which have a strong smell, you can think of bleach. In bleach is actually chlorine, the gas that's coming out, where you have that like that stench and like, you know, like it's very strong. Alright? So oxidation, right? So when something is oxidized, the oxidation state increase. You have fancy mnemonic to remember it, you know, but because I don't want to use anything to a mnemonic and then probably in the exam you don't remember the mnemonic, you're confused. Because it's actually something that you can understand. Alright? So the oxidation state increase, so it means that A would go to A plus. That's oxidized, right? So the oxidation state in 0 plus an electron. Right? It simply means that if the compound is oxidized, it will actually be losing electron, right? And oxidation state increase. Right? So if we look at the number line -2, -1, 0, +1, +2. Sorry, just 0, not -0, alright? All the elements, this is all elements in your free state. So like oxygen, hydrogen, chlorine, they all have oxidation state of 0. Alright? Now, so for example, we go and we form like calcium oxide, right? We can see that the calcium is 2 plus, the oxide is 2 minus. Alright? So, if we should be having a reaction like calcium plus oxygen to form calcium oxide solid, you can see that this would be a 0 plus 2, and this is minus 2. You can see that in terms of this case that the calcium will move from 0 to 2 plus an electron, right? While the oxygen plus 2 electron will go to 2 minus. Following? I'm just using this reaction to break down oxidation reduction. Alright? So it simply means that calcium would increase in oxidation state. So it is oxidized. So this is 2 electrons just to be correct, accurate. Right? So the calcium would increase in oxidation state from 0 to 2 plus, so it would be oxidized. Right? While the oxygen it would move from 0 to 2 minus, so it would be reduced. Alright? Now, for our oxidation reduction reaction, one of the element or compound, the element or element in the compound must be reduced, or the other one must be oxidized. That's how the redox reaction will work. Alright? So now, oxidation reduction process. The compound, the element that is causing the other element to be oxidized is the oxidizing agent. So agent would be like the one causing something to occur. Alright? So that is why if we talk about oxidizing and reducing agent, the calcium is oxidized here. So what is causing it to be to be oxidized would be the oxygen, so the oxygen would be referred to as the oxidizing agent. Following? So the element that it's carrying up, causing the next element to be oxidized would be the oxidizing agent. Likewise, oxygen is being reduced from 0 to -2, so the calcium that's causing that reduction would be the reducing agent. Alright?